understand now another measure of association. Again, when I say association, I mean linear association between two numerical variables. We have already seen the measure of covariance, but recall when we talked about covariance, we said that the covariance is difficult to interpret because the covariance has units. So, I am going to another measure of association, and this is what I term the correlation between two numerical variables. What is a correlation? It is another measure of linear association between two numerical variables. It is derived from the concept of covariance. We have already introduced the concept of covariance. Now, how do I find the correlation between two numerical variables? Let me call those two numerical variables x and y. Again, going back to our example, you can see that I have this example here where I have size and price of a house. There are 15 observations. So, if you can look at this, let me zoom it a bit more. So, you can see that I have the size and price. So, x is my explanatory variable, which is the size of the house. Y is my response variable, which is the price of the house. So, if I want to know the correlation between these two variables, I can represent it by R, or some books represented by rho, the Pearson correlation coefficient R between variables x and y. I can drop this x and y also and just represent it by R. The Pearson correlation coefficient is given by R, denote the covariance between x and y divided by the product of the standard deviations of x and y. Since I have already said that it is derived from the covariance, a more formal way of defining the correlation is the following. I can have in my numerator, again I have x minus x bar and yi minus y bar. These are nothing but the deviation of x from its mean, and this is the deviation of y from its mean. I sum it up over all data points. I have total number of data points is total number of observations. This is my small n here. Okay, I am summing it up. In the case of my example, n equal to 15, because I have the data on 15 homes. I am looking at the sizes and prices of these 15 homes. I divided by the squared sum of deviations. This is the sum of this is the squared deviation, sum of squared deviations of x, and this is the sum of squared deviations of y. In other words, I also have that this is equivalently, I can write that this is equal to the covariance of x and y, which is given here, divided by the product of the standard deviation of x, which is represented by s of x and s of y. So, this is how we compute our correlation between two numerical variables. Okay. Now, why is it important? Now, when you look at this term covariance x, y, I know that the covariance term, again go back to the way we defined our covariance. We saw that when we looked at the covariance term, this is how we defined our covariance term. We looked at the deviation. Okay. Now, the deviation, for example, if x is measured in terms of square feet, the deviation is also going to have the unit of square feet. Y is measured in terms of INR. The deviation also is in terms of the currency, which is in lakhs of rupees. So, this correlation covariance term has a unit, which is the product of the unit of this variable and this variable, which is square feet into Indian national rupees. Now, when I look at the correlation For the same variable, I have defined the correlation as the following. Covariance. Now, what are the units of covariance? Covariance, in our example, the units of this covariance is square feet, which is the unit of size, which is my variable x, and then I have, which is INR in lakhs of rupees, which is the unit of price, which is my response variable y. Now, if you look at the standard deviation of x, standard deviation of x is also going to have the same units as that of x. Standard deviation of y is going to have the same units as that of y, which is in Indian national rupees. So, you can see that the units cancel off when I talk about a correlation measure. So, this measure of correlation is a unitless quantity, but we need to also remember that it is a measure of linear association. It can be shown that this correlation coefficient always lies between +1 and -1. Okay. So, now we have a covariance measure and a correlation coefficient. Now, how do we use this correlation coefficient to tell about the strength of the association between my variables? So, recall, when we looked at the covariance matrix, we started by what we said was a scatter plot matrix. In the scatter plot matrix, I have my explanatory variable, which is on the x-axis. I have my response variable, which is on the y-axis. So, if I have a scatter of this kind between these two variables, okay, I am just looking at one of the quadrant, but I could have in both the quadrants, but I am just for exposition's sake, I am just looking at this quadrant, and suppose I have my x bar. So, x varies from this point to this point. So, suppose this is my x bar, that is the mean of my first variable, and suppose this is my y bar. Okay. Suppose this is my x bar and this is my y bar. We further said that we could split this entire scatter into 4 pieces. In this piece, if I am going to have all my points orange, this is this piece, that is where my, so if I am going to shade this region or this points, so all the points in this region are basically points where my xi minus x bar and my yi minus y bar are both greater than 0, because all the points are greater, both my x point and my y point are greater than the respective means. Now, in this green area, green shaded area, my xi minus x bar and my yi minus y bar are both less than 0, because both the xi points and the yi points are less than their respective means. Now, if I look at the purple area, which is this scattered plot, I find the yi's are greater than the y bar, whereas my xi is less than the x bar, and in this final area, which is say purple, the smaller area here, I have here xi minus x bar is greater than 0, whereas yi minus y bar is less than 0. Okay. Now, let us understand why this correlation metric or this correlation coefficient becomes very important. Now, suppose I have my data set of this kind. Okay. Suppose I have my data set of this kind, where I have a tightly clustered data. So, remember when we talked about association, we wanted to see the direction and whether it is tightly clustered, whether there is a variability, all these points. Suppose it's a tightly clustered data. For this same data point, if I continue with the exercise I have done before, this is my x bar, this is my y bar. So, you can see that in this I have very little points which are here, but majority of the points lie in this area and in this area. The product, so when I look at the product of the deviation, it is greater than 0 in this quadrant. The product of the deviation is again greater than 0 in this quadrant. Hence, the sum of the product of deviation, which is xi minus x bar by yi minus y bar, because the product is always greater than 0, the sum is going to be greater than 0. Hence, this type of a pattern will always result in a positive covariance. Whereas, if I have my data which is of this kind now, I have my x here, I have my y here, and my data is of this kind. Suppose this is my scatter plot. Again, this is my x bar, this is my y bar, this is my x, this is my y, this is my x bar. I have the same y bar. Now, if you notice this scatter plot, you can see that the product, here I have a product. So, if I look at the product of these coefficients, the product of the deviations is greater than 0. Here the product is going to be greater than 0 in this quadrant. Here the product is going to be less than 0. Here also the product is going to be less than 0. So, what we notice here is the product of the deviation. So, xi minus x bar into yi minus y bar in this portion is going to be less than 0. In this portion is also less than 0. I do not have any points in these two areas. So, the summation over all my data points, the total sum of my product deviation is going to be less than 0, and this resulted in a negative covariance measure. Now, if I am going to divide them by their respective standard deviations, I get my correlation measure. So, the correlation measure always is between -1 and +1. How do I interpret this correlation measure? If there is if the data is of this kind, my covariance I know is going to be positive. I divided by the standard deviations, and I see that if my data is of this kind, then my correlation measure is very close to 1. Whereas, if my data is this kind, my correlation measure is very close to -1. Okay. So, this is a perfect linear relationship between x and y in the positive direction. This is a perfect linear relationship between x and y in the negative direction. Before I go to this data set, let us work on a small hypothetical example. Again, I had x which was my age, y which was the height. I wanted to explain whether as people grow older, their heights increase or decrease. I wanted to know what is the association. So, we found out what was the deviation. So, I knew the mean here was 3. Okay, we computed the mean here. This is what we already did. This is what we did in our. So, my mean was a 3. And the mean here was a 92.6. Okay. So, the deviation was 1 minus 3, which was -2. The deviation was 2 minus 3, a -1. 4 equal to -2 whole square, -1 square is 1. So, this is the sum or the square deviation is what is given here. Similarly, 0, 1 and 2, this is giving me the square deviation. Similarly, 75 minus 92.6, I also computed that as -17.6. The square of -17.6 is equal to 309.76, and this is giving me the squared deviation of each of my y observation. This is the sum of squared deviations. This is the sum of square deviations of y. This is the sum of the product of the deviations. Okay. So, if I apply my first formula, the correlation coefficient is nothing but the numerator is the sum of the product of the deviations, and here I have the sum of square deviations, both of them, and sum of square deviations of y, both of them under square root. Sum of total sum is equal to 82, okay, divided by square root of 10 into square root of 677.2. In using the second formula, which is nothing but covariance divided by standard deviation. What is the covariance of this value? We have already computed the covariance. You know the covariance is 20.5, covariance between x and y. This is something which you have already computed. I compute what is the standard deviation of x, which is 1.58, standard deviation of y, which is 13.01. I divide it and I get 1.58 into 13.01. Hence, this 0.9964, which is very close to 1, captures the strength of the linear relationship between age and height. So, the strength of the linear relationship, this is a positive, very strong linear relationship between age and height. Now, let us go to the next example. In the next example, I looked at the age of a car and the price at which it is being sold. We know as cars get older, the price at which they are being sold comes down. So, again my price is recorded in lakhs of Indian rupees. So, as the age of the car, as my car gets older, my price comes down. Again here I compute, so this was again a 3. So, you can go back, this is what we have here. I had a 3, this the mean. So, y bar was 4, x bar was 3. I compute the deviation. So, I have a -2, -1, 0, 1, 2, and this is the square of the deviations which I have here. Here again I have a 2, 1, 0, -1, -2. Again the square is 4, 1, 0, -2 square is 4. The product is -4. So, this is a -4, -2 into -2, which is a -4, -1 into 1, which is a -1. So, again the numerator term, which is the sum of the product, cross products, are equal to 10. Then I have the square root of the sum of x deviations, which is equal to square root of 10, the square root of yi minus y bar whole square, this is again square root of 10. Hence, I have my first correlation matrix, which is -10 divided by square root of 10 into 10, which is -1. We already have computed the covariance as -2.5, okay, which is 10 minus 10 by 4. Again remember it is -10 by 4 when I am computing the sample covariance, where I am dividing it by n minus 1 instead of the total number of observations. So, hence I am taking it to be -2.5. The standard deviation is 1.58, and I can see that 1.58 into 1.58, I am going to get something which is close to -1. Okay. So, we have already seen from the scatter plots of both of these, this has a, so with age, which is 1, 2, 3, 4 and 5, 3, 4, 5, 6, I have these as my points 2, 1, 2, 3, 4, 5, 6. 3 is a 4, 4 is a 3 and 5 is a 2. So, you can see that the as my car gets older, the price drops and there is a perfect negative correlation between age and price. Okay. So, I do not have to specify the units when I am talking about a correlation measure. So, now let us use how do we compute correlation using Google Sheets. So, to use the Google Sheets, what we do is first we go to any cell. Okay, let me enlarge it a bit. I go to any cell here. So, what it asks for is data y and data x. What I need to specify is what is my first data, which is my x data, which is size in this case, and my second data, which is my price, which is my C2 to your C16. So, the correl measure returns what is called the correlation coefficient or the Pearson correlation coefficient between the two variables. So, we can see that the Pearson's correlation coefficient between the variable size and price is 0.804. Similarly, let us look at the correlation coefficient between the next data set. Again, what we had in that data set was a size and price for a different data set. Again, I find what is the correlation coefficient. My data here is B20 to B34 and C20 to C34, and I immediately see that the correlation coefficient is 0.149, which is very close to 0. The third data set was age of a car versus price of a car. I repeat the same here also, and I look at the correlation between the two variables here, which is going to be the age of a car and the price of a car. So, this is B. So, I just look at it. So, let me look up to B50 alone, and I notice that this correlation coefficient, the correl, okay, the correl between these two is what I am going to notice here is given by minus. So, if you look at the data, you see it is a minus 0.927, which is also a large negative value close to -1. Now, one way to explain what is happening here is by looking at the scatter plots. So, let me look at the scatter plot between my first data set. So, again I plot a scatter plot between my first data set, and what I notice in my first data set and the scatter plot is there is a reasonable linear relationship between my x variable, which was the size here, and my y variable, which was the price, and this strength of this linear relationship is what is captured by my correlation, which is given by 0.804. When I do the same scatter plot for the next data set, I again go back and do the scatter plot for the next data set. What I observe in this case is that even though the variables are the same, what we observe in this case is the scatter, there was a pattern which was evident in the first data set. I don't see that pattern here, and there is no pattern here which is reflected in my correlation coefficient, which is very low and close to 0, which is a 0.149. If I continue and do the same thing and plot a scatter, in this scatter plot I see a negative decreasing trend, and this quantifying or the strength of this negative relationship is quantified by this number minus 0.924. 7. Hence, we can see that the correlation coefficient quantifies the strength of the linear relationship between my variables. In other words, based on the correlation measure, I can tell the following that A, the correlation measure lies between +1 and -1. So, I can have, so it can take any value. So, if it is, this is a 0.5, this is a -0.5, this could be a 0.75 minus 0.75, this could be a -0.25, this could be a +0.25, this could be a +0.75. So, I can start telling the following that if I have data, my correlation measure is between 0.75 and 1, then I could say that this indicates a strong positive linear association. Similarly, if I have a correlation measure which is in this range, this could indicate a strong negative linear association. This association was my first example of size versus price of a home. This was the example of this kind of a relationship was age of a car versus price of a car. Okay, and depending, so this is a very strong, this portion could be just a portion where I have a reasonable positive and reasonable negative. This could indicate a weak, and between these two, this range could indicate no association. These are just indicative measures to say whether or to interpret how strong is my linear relationship. So, once we do this, we come to an end of this section. First, we introduce the measure of correlation, and then we saw how to interpret the strength of a linear relationship by using this measure of correlation by seeing where the measure lies.